on this computer. Second, Jamboard. And finally, share screen. Okay, problem number 2, room 1. You are up.
So our problem was a bag of basmati rice has a mass of 0.252 kilograms. So to find the weight on Earth, we just went through the same process that we did for the dog. And we wrote what we knew, which was the mass was 0.252 kilograms. And the Earth's gravitational field strength is 9.81 newtons per kilogram. And what we want is the force of gravity on the force of gravity, which is the gravitational field strength on the mass, which is basically just the weight of the bag of rice. So then for the relationship, we use the same kind of equation that we made in class, which was the force of gravity equals the gravitational field strength times the mass. So then we just plugged it in over here, and we got that the weight of a bag on Earth is approximately 2.47 newtons.
Awesome. Anybody open to the class? Like questions, feedback? This is a great answer, by the way, right? So I'm just going to start there. That's a great answer. How do we make this a awesome? Is there anything that you would do better on this Jamboard? Like, is there anything that you can think of that could be better than what they've done? I mean, what they've done is really good. Is there something you can do better? There's one thing you could have done better. One place. Yeah, Ian.
Maybe they could have organized it just a little bit better. I don't know. It's kind of like all over the place. I mean, it's
a little bit of, no, that's fair, Ian. That's a good comment. So that's not what I would think about. Maybe there are two then. Whenever you put a number, you put a
unit.
Unit. Is there any place on there where there's a number with no unit? And hashtag, can we fix it? And it is now officially awesome. Cool. Room number 2.
We kind of had the same approach in that we like kind of addressed like what we know, being that Earth's gravitational force is 9.81 newtons per kilogram, and then also that our person had 518 newtons exerted on them.
Mm-hmm.
So given that, we made the equation that you see on the bottom of the screen, which ended up getting us about 52.8 kilograms since the newtons on both of the units, I guess you could say, canceled out, which corresponds with our want, which is the mass of the person.
That's awesome. Cool. So there's one thing, and again, like I'm just going to be picky here on purpose, right? Just because I've never worked with you, and so the only thing that I would do differently a little bit is here. You see how you wrote n equals 9.81 m, right? So I'm assuming m stands for mass. Is that correct? Elia?
I didn't actually write that part, so I couldn't.
Okay. So who else was in your group? Who wrote that part?
I think it might have been Ruby.
Ruby, what do you think? Is that what you wanted to? Is that what you wanted to say?
Yeah, I think so. All right, no,
that makes sense. That makes sense. Like that's what. So what was n for then?
Newtons.
Yeah, that's what I thought. So you see how in that equation you have on one side a unit, newtons. And then on the other side, you have a variable. So what I would have loved, what would have made this like one step better would be something like this. That's a force equals 9.81 times a mass. And that's all about variables. And then we know that force is in newtons, and we know that mass is in kilograms. So I guess what I'm trying to get at is when you guys write equations, try to write equations using variables and not units. So anytime you're tempted to write N for newtons, say, let me write F for force instead, or FG, or whatever you want to call, or W for weight, whatever you want to call it, right? But don't mix units and variables. But otherwise, this is perfect. Thank you. Ruby and Marlo, if you could stay with your camera on, that would be great. Okay, room number 3.
So I can do this one. So our question was so at the summit of Mount Everest, we have a set of data right here that shows how much various masses weigh up there, and the question is it the same as the 9.81 newtons at bay? And we said it was yes, because even though the mass of 1 and the 8.4 don't match up, if you put it all on a graph as we did on the right, then and you use the line y equals 9.81x, we got that from the 9.81 newtons, then it lines up as what seems to be a line of best fit. And we decided that that fit as good as any, and that they were the same, and that height doesn't really affect that in this case.
Cool. So this is a question from me as somebody who's never worked with Desmos and doesn't understand Desmos very well. Does Desmos, if you ask Desmos to make a line through the points, will it actually give you an equation?
I don't know how to do that, but we just put in the line y equals 9.81x and it matched.
Got it. Somebody else was about to talk.
No, that's fine. That's what I was gonna say.
Okay. Okay. So what I did when I first started saying what I did is I actually made a spreadsheet using the same numbers that you guys had, right? You guys see the spreadsheet?
Yeah.
Okay. And what I did is I, again, like clicking on the numbers, right? What I did is I made sure that I added a trend line, right? So this was going like that. So what I can do is I can add the trend line. I said use the equations. That gave me the equation. And what you see, and the other thing that I did is I made sure that I would see my y-axis so I can see where the y-intercept is. So notice that here, for example, you don't see, the y-intercept is negative. So what I'm going to do is I'm going to put, like, instead of doing 0 here, I'm just going to double click on the 0. See, there's a minimum value. I'm going to put something negative. So like minus 0.5 or something. No, that's not going to work. Minus 1. Minus 1. Okay. So, whoa. Really? So minus 1, it didn't like that. So, but anyway, now you can see that there's an intercept that's negative. So, and if you look at the equation is 9.77. There is no way you would have been able to see that. Like if you just wrote 9.81x on Desmos, you would have seen a fit that was pretty close because the difference is very, very small, right? So your strategy was not a bad one. It's just not a super accurate one. So next time, if you have this kind of problem, just make a spreadsheet and solve it that way, and you'll get a better solution.
Yeah, I didn't know the spreadsheet had that feature. So.
Totally. Yeah, no, absolutely. And again, this is like, I don't know what you guys did last semester. So I if you didn't know that, that's totally fine, right? But try to use a spreadsheet. So what I'll do is I will copy that. I will put this on your, let's see, where is it? Jamboard over here. See, I'll do that, please. No, really? It's disappointing. Okay, whatever. I'll do it later. Okay, room 4. Who are you?
All right. So for ours, we went with let me actually take a look at the problem real quick. So we took the rock's weight on the moon and divided it by the amount of newtons per kilograms on the moon to get the number in kilograms.
Mhm.
And then we multiplied that by the gravitational strength on Earth. And we got that the rock is 13,124 newtons on Earth.
Love it. So again, good answer, right? Can we make this better? Thoughts? Layla?
Well, kind of like the same mistake you found on my groups. I think maybe you can add the units into the equation too.
Yeah, right. So 25, 2,200, 22,000, 2,250 with a unit, right? 1.63 with a unit. But I love the fact that you were able to go from like the values on the moon to the mass, which is the same everywhere, to then the weight on Earth. But make sure you put units, okay? That was great. And room 5.
So our question was, a rock has a mass of 5 kg on the moon. What is the mass of the rock on Earth? We know that the gravitational strength is 9.81 newtons over kg, and the mass is 5 kilograms. The gravitational strength on moon is 1.6 n over kg, and we want to know the mass of the rock on Earth.
Cool.
So our relationship was mass equals kilograms divided by gravitational strength of the moon, which is 1.6, and then times gravitational strength on Earth, which is 9.81. And then we did the math, and it turned out that the mass was 30.4 newtons per kilogram on the Earth.
Okay. Thoughts about that from the rest of the class? Do we like this answer? Do we not like this answer? Jordan, you looked like you were about to say something. No? Ian loves the answer. He put a thumbs up for it. Ollie's vouching this answer. So people who did the previous problem, right? That's Ollie's group, right? Do you see a flaw somewhere in here? People who did the, because it's related to the other problem, right? I mean, we're having something on the moon, we're having something on Earth, and we have to do the transfer, right? So if you look back to what happened on room 4, what was their reasoning? Like, again, forget the numbers for a second, right? Forget the numbers for a second. Think about the reasoning. What did they do? What they find a relationship between? They said that somehow the weight on the moon was related to the mass on the moon. Yeah. And then what did they say? What did the second equation say? Yeah, Leila?
They can use that mass and the Earth's gravitational field strength to find how much it would weigh on Earth.
Yeah, so they had a relationship. They said, we know there's a relationship between the weight on the moon and the mass on the moon. And then they said, we know that there's a relationship between the mass on Earth and the weight on Earth. And what did they use for the mass on Earth? How does the mass on Earth compare to the mass on the moon? Yeah, Dak.
Shouldn't it stay the same?
Well, does it on this slide?
No.
It doesn't?
Or no, yeah, sorry, it does, yeah.
It does, right? They're 1,380 kilograms
Mm-hmm.
on both planets, or both like, you know, whatever. You can decide whether it's fine or not. So why is that true? Why can they say that the mass on Earth and the mass on the moon are the same? What does the mass depend on? Yeah, Layla.
The mass depends on like how much there is, or like I think the weight depends on how much force is pushing.
Right, so the weight depends on how much force is pulling on it. The mass only depends on how much stuff there is. Question is there a different amount of stuff on the moon and on Earth? And the answer is no, it's the same object, right? So then I want you to think about this. If a rock has a mass of 5 kilograms on the moon, what is the mass of the rock on Earth? Noel, what do you think?
The mass stays the same because it's not affected by the gravity.
The mass is the same because it's not affected by gravity, right? So the and the reason why you had a problem is because that relationship that you found here, that's the problem. Look at your relationship here. You're saying kilograms divided by 1.6. That's a force, right? I think. I guess what I'm saying is that I don't know that that relationship really works. So make sure that you use relationships that you actually do know exist, like for a fact. And the only relationship we have is F equals mg, right? F equals GFS times m. That we know for a fact works. That one may or may not work, right? But it did lead you astray. And the fact is that the mass should be the same for on all like planets, because the mass is just an amount of stuff. So good work on this. So here is your, so first of all, let me stop recording. Stop.